Hello everyone, this is Dr. Zach. We're going to review integration with our trigonometry today through a couple of examples. Complete your lesson preview, then we will discuss the ideas necessary to find these integrals. For our first question, did you use the trig identity sine squared 6x is equal to 1 minus cosine 12x divided by 2? Remember, you had to double that angle because of the way our identity works. Afterwards, you're going to rewrite your problem as 1 minus your cosine 12x divided by 2. That will all be squared. Here's my dx. Did you factor out your 1/4 and rewrite the problem so that you have 1 minus 2 cosine 12x and then plus the cosine squared 12x. From here, you're going to have to use another identity, and that identity is going to be your cosine squared 12x is equal to 1 plus the cosine, double the angle, 24x divided by 2. Substitute, and then you'll be able to integrate. For question B, do you recognize that this problem is going to take some trig substitutions in order to find our integral? Notice the 36 is going to be an indication that the length of the hypotenuse will be 6. The side opposite of theta is x, so we know that our missing side is the square root of 36 minus x squared. From here, we write that the triangle sine of theta is equal to x over 6. We can solve for x. Now, dx is going to be equal to your 6 cosine theta d theta. We're ready to substitute in for x squared and for dx. However, let's take a look at the square root of 36 minus x squared and find its equivalent. It's going to be the square root 36 minus 36 sine squared theta. Underneath your square root, you will have a 6 on the outside, square root 1 minus your sine squared theta, which gives us a lovely cosine theta when we substitute. Ready to take all the pieces, put them into our integral. X squared is your 36 sine squared theta divided by your square root, simplified to become 6 cosine theta. And of course, dx was equal to your 6 cosine theta d theta, which leaves us with the integral of 36 sine squared theta d theta. Once again, we're going to rewrite our problem using a half angle identity. So we have 36 times 1 minus the cosine 2 theta divided by 2, and then we have d theta. We integrate at this point, and we have 18 multiplied by theta minus sine 2 theta divided by 2, and then we add c. However, we know we can't keep our theta values in there. Go back to our original problem where we set up the sine of theta, solve for theta. We get 18 times the arc sine of x over 6. Now we have to figure out the sine of 2 theta, and we want to use our triangle in order to help find that value. Another trig identity for us to know would be the sine of 2 theta is equal to 2 sine theta cosine theta. And we know from our triangle that the sine of theta is x over 6. Let's substitute that in. And we know that the cosine of theta is the square root of 36 minus x squared divided by our hypotenuse, which is 6. So that'll leave us with x over 18 times the square root 36 minus x squared. Now we'll substitute the values, the expression for sine 2 theta, into our final answer and come up with. For our first example, we're looking for the arc length of our curve. So please recall what the formula for your arc length is. Your arc length formula will be the integral from a to b, assuming that we're going to use x values, of the square root 1 plus your dy dx quantity squared multiplied by dx. So for our problem, dy dx is going to be equal to x. So then when we square it, of course, that's going to be x squared. Substitute, we're going to have the integral from 0 to 4 square root of 1 plus x squared dx. Once you see this problem, you should recognize that we will need to draw a triangle in order to integrate using trig substitution. Theta is our angle. We have the hypotenuse that was given to us as 1 plus x squared. I'm going to label the opposite side x and the adjacent side 1. From here, we write that the tangent of the angle theta is equal to x over 1, or just x. From that, we know that dx is going to be equal to the secant squared theta d theta. Moving right along with this, we know the square root of 1 plus x squared. That square root expression can be rewritten as the square root of 1 plus tangent squared theta, which simplifies to secant squared theta, take the square root, and we have secant theta. So this is making a very nice little problem. We're going to integrate from 0 to 4. We have secant theta replacing the square root 1 plus x squared, and our dx is going to be the secant squared theta d theta. All right, from our last lesson, this secant cubed theta should look so familiar. We're going to do integration by parts in order to figure it out, and we know from our last work with this problem, we have 1/2 secant theta tangent theta plus 1/2 the natural log absolute value secant theta plus tangent theta. Now we're ready to go back to our triangle, substitute in. We know that the secant of theta, according to the triangle, is going to be the square root of 1 plus x squared, and the tangent of theta is x. Plus, and we'll have 1/2 natural log absolute value, again, the square root 1 plus x squared, and next we will have a plus x. Once we have the x values back into our problem, we can take our answer and substitute 0, 4. So go ahead and complete this question. Let's take a look at example 2. Go ahead, read the question. Did you notice that your equation was already given to you? The toughest part about this particular problem is keeping track of all of your constants. So R is a constant, capital R. We have M is a constant, capital L is a constant. The variable that we have is little r. So we're going to integrate this problem with respect to r. Did you notice that our problem is to the 3/2 power? So with that in mind, we're again going to draw a triangle. And when we look at our triangle, we're going to label the square root of r squared plus l squared as the hypotenuse. Across from theta is the variable r, and then we have l. How does that help us? The tangent of theta must be equal to r divided by l, so we will have l multiplied by the tangent theta. dr, when we substitute, is going to be l secant squared theta, d theta. Next, we want to substitute into our equation. Into our integral, we have 1 over capital R integral from 0 to r. We have the 2ml. Let's put that outside. 2ml is now outside. Now 1 over your r squared plus l squared. We didn't work that out. Let's go back. We have the square root r squared plus l squared. And when we do our substitution, we get the square root. Your r is going to be l squared. Here's my tangent squared theta plus l squared. Factor out my l. I'm left with the tangent squared plus 1, which is secant. So I've got secant theta. Go back to my problem. I'm ready for that substitution now. When we substitute, we have 1 over r squared plus L squared. The square root of that is going to be cubed, which gives us an L cubed secant cubed theta. dr was L secant squared theta d theta. So we're left with 2m over r. One of our L's will be remaining in the denominator. Then we have the integral of the cosine theta d theta. And the antiderivative of your cosine is going to be sine. So we have 2m over rl times the sine of theta. Oh no, we need to get rid of that theta, don't we? Okay, so go back to your original picture. We have sine of theta. Replace with 2m over big RL. Sine of theta is going to be r divided by the hypotenuse, which is square root r squared plus L squared. Now let's integrate from 0 to capital R. Substitute the capital R in. You're left with your 2m over r. L. You have big R divided by square root big R squared plus L squared. Substitute the 0 in. You get 0. And ta-da! You have completed this lovely problem. All right. You should be preparing for your upcoming test. Make certain that you give these 6 questions a good try. Have a great day.